Okay, so far we've talked about the different types of criteria air pollutants that are monitored by the EPA in the Clean Air Act, right? Uh, let's see. So where do all these pollution coming from, or what are some of the sources? Well, there's some are so air pollution, by the way, is anything that's in the air that we don't want. Like it's either harmful to our health, or it might affect our the visibility or and things like that. So it's not necessarily all man-made. There are natural sources as well. So for example, volcanoes will emit a lot of nasty stuff: sulfur dioxide, particulate matter, carbon monoxide, nitrogen oxides, right? And these sometimes could have an impact. Like I think Mount Helens erupted. The area suffered acid rain from the sulfur that was produced, and then all the particulates from the and ash and things that might be produced from it. We talked about this when we talked about the nitrogen cycle, how lightning is a abiotic nitrogen fixation process, right? Combining nitrogen with oxygen in this high temperature situation that you might have in lightning. Forest fires is combustion, so you can have particulate matters, carbon monoxide, and nitrogen oxides. And plants actually produce natural volatile organic compounds, VOC. So when you see this haze, this beautiful haze in the mountain, this is actually VOCs. This is actually something that's equivalent to smog, but this is it's all natural. Okay, so nature could be polluting too sometimes, and these can react with sunlight and produce ozone and things like that as well. Well, but we remain, there's not much you can do about some of these things, these natural emissions. Maybe I guess forest fires could be our fault too. But we're mainly concerned about anthropogenic emissions because these are the ones that we produce, and oftentimes those are more harmful in many ways. You don't need to memorize it, but you should kind of know generally where most of these come from. So this is a graphic just kind of showing you the sources of these criteria air pollutants. So this one's carbon monoxide. Where does carbon monoxide come from? It's coming from cars, right? On-road vehicles and other equipments, unless they're kind of like fires and things like that, right? So this is outdoor, by the way. This is a little bit different. When we talk about indoor air pollution, carbon monoxide is an indoor air pollutant as well, and that has different sources. It's obviously not cars, right? But outdoor air pollution, ambient air, on road vehicles. Nitrogen oxide, the NOx, right? Again, cars, number one, and other equipment. Electricity generation, because they're combusting at high temperatures. This is all different forms of combustion, right? That produces nitrogen oxides. Sulfur dioxide, because it's mainly coming from combustion of coal, electricity generation is going to be the big one. And then this is particulate matter. It's got a lot of different sources. Could be just dust, miscellaneous things. Right, so that's particulate matter. So the EPA sets these standards for how much of the each of these criteria air pollutants are allowed, and that's called the NAAQS, National Ambient Air Quality Standards. So note that it's ambient air quality. So ambient means that it's outside air. So this cannot say anything about what's happening inside your house or inside buildings. This is just strictly outdoor outdoor air quality. There also, this is not in your book, I'm not quite sure why. AQI, which stands for Air Quality Index. This is more kind of an instantaneous measure of air quality. So you can actually look up if you come AQI .gov. I don't know if you just search up AQI. EPA has a site where you can look up your area and then what the AQI is. These are generally based on how much ozone and particulate matter in the air. So like right now, this time of the year, there probably isn't too much ozone because it's still kind of cool and it's still early in the year. But when you get into like the heat of the summer, uh, the air quality index might get pretty high, and it's mainly because of ozone. And depending on what's going on with the weather and what's going on around you, might have particulate matter as well. Okay, so that's what there's different index and standards for pollutants in the air. Okay. You need to understand about, let's see, this is getting into smog formation. This is photochemical smog, mainly ozone. Okay, so photochemical smog, right? So remember we talked about different types of smog. There is the uh, the the gray smog, the London type sulfur smog. This is not a photochemical smog. This is just sulfur in the air. And then you got this brown smog, right? Which is, this is a photochemical smog. This is mainly ozone. Okay, this is still a challenge in many urban areas. So we've, kind of, clean up the air, and we have less sulfur, we have less particulates in the air, although it really varies from place to place. There are some places that still, very poor air quality index because of particulate matter. Ozone continues to be a challenge in trying to deal with them. I think the opening story in Chattanooga, they were able to do a pretty good job, cleaning the air, but now they're just dealing with ozone because and EPA keeps reducing, the tolerant level, and they're having a hard time kind of keeping up with that. This is produced by nitrogen oxide in presence of sunlight. It creates ozone and nitrogen oxide. So this is just a chemical reaction. I guess it's not really, this is not a balanced equation by any means, but here there's actually a better, this is the, I don't know if this is one's balanced either. But yes, you need sunlight for this reaction to happen. Right, and what it produces is ozone in the end. So this is the daytime ozone. So when you have lots of sun and you have lots of nitrogen oxide, like so in the summertime in the city, or sometime in suburbs where there's lots of cars, you can have high levels of ozone, right? But what happens at nighttime when there's no sunlight, or I guess it can happen anytime, this just doesn't require sunlight, the ozone breaks back down, so that the reaction reverses. Right, so I guess this is the, this is an endothermic reaction, this is exothermic reaction, and what you get is oxygen back and nitrogen oxide back, right? So, and this is kind of more or less at equilibrium, right? Now, what happens when there are VOCs present, which is another one of those pollutants, is that when you have VOC present, this combines with the nitrogen oxide. So if it combines with the nitrogen oxide, so you still have this reaction and you still produce ozone, but then you can't have this happening because this is gone, right? That means you're going to have accumulation of ozone in the environment, and that's why VOC is involved in the formation of ozone. Okay. Yeah, so that's what that is, and this doesn't require sunlight. This part right here, I don't think so. Okay. Also, in general, this is true of all chemical reaction. Higher temperature increases the rate of chemical reactions, and this is the reason why ozone is a bigger problem in the summertime. Okay. Another factor that could really affect pollution is a weather phenomenon called thermal inversions. Thermal inversions generally happens in regions that are in depressions or surrounded by mountains, so they're in a valley or in a depression, and it's the reason why it's called inversion is because the temperature is inverted. So normally, this is normal conditions, right? It's warmest at the surface, and as you move up, it gets cooler and cooler and cooler. So this is a temperature profile here. The temperature is highest at the highest at the surface. What? Altitude is this way, so you go moving up. The temperature is highest, I'm sorry, here you go. Highest at the surface, and then as you move up, it gets colder and colder and colder, right? During temperature inversion, what happens is you get this cool air kind of, because cool air is dense, it kind of slides down the mountain overnight, and it kind of slips underneath a layer of warmer air. And you get this, this layer of warm air sitting on top of cool air, because cool air is dense, and it traps pollution. So if any pollution that happens in here, it can't escape because there's this ceiling up here. And the reason why it's called inversion is because now it's not getting, normally it gets cooler and cooler and cooler as you go up, but instead you go up and it gets warmer. So I mean, it does eventually gets cooler, but this is what happens. And let's see, I have Wikipedia, actually, of all places, have pretty neat pictures of some of these inversion photographs. So here is, I don't know, where some in Iceland or Ireland or something. You see this layer here? So here, and notice the mountains in the background. There is cooler air that kind of slipped down and is sitting here, and then there's warm air sitting on top of it, and then you can tell because of the smoke that can't keep going up because of this this warm air ceiling that's sitting on top. Again, an ocean. Where is this? This too. This is a city underneath here. There's like city. All the smog is trapped underneath this layer of warmer air sitting on top, and you can imagine how bad the air quality in this area is because of that, right? Let's see if you got other pictures on here. This is kind of interesting because it's colder air sitting on top. You can see this, the trees are frosted here, right? And then up here, because the air is warmer, the frost is not there. So this is not really showing you so much the air pollution, but it's kind of showing you how the stratification of the temperature is very visible here. This is, I think, in Shanghai, or one of the cities in China. Again, you get this plume of air pollution that is being trapped by the layer of warm air on top. Okay, so that's temperature inversion, and it is a weather phenomenon that can exacerbate air pollution scenarios. Okay, let's see, I got 3 minutes. Real quick, acid deposition, and we talked about this when we talked about the water aspect of it, but because the source is the air, right? It's all, that's why it's in this chapter. So the primary pollutants are sulfur dioxide, nitrogen oxide that reacts with water and then comes down as acid precipitation, right? And some of the effects of acid rain, and again, I think we talked about this before, so I guess I don't need to get into it too much, right? It lowers the pH of lakes and streams and the soil as well. Although a lot of it might depend on the parent material. If there's a lot of limestone in the soil, then that's going to buffer the pH, and you may not see as a big effect. But if it's more of a granite or quartz-based soil, or the parent materials, then it's the lower pH of the rain is going to directly impact the streams and lakes, in which case it's going to end up affecting some of the organisms that live there. Amphibians are very sensitive to pH. They can't reproduce when the pH is too low. Remember, I also mentioned earlier in the earlier chapter that the acidity is not so much itself toxic, but it releases metal ions. It mobilizes them, and that makes that is toxic to fish and some trees as well, and that's the reason why they are weakened or killed by acid rain events. Buildings too. So these buildings. I mean, these ancient buildings lasted thousands of like over 1,000 years, but then within the last 100 years or so, it's degrading because of acid rain. Anything that's made of marble or limestone, buildings, statues, monuments, and things like that are crumbling because of the acid deposition. Acid also affects paint surfaces too. So like the paint on cars and things could actually be degraded by acid deposition as well. Okay.